Okay, let's go. Number 1. The Proxima Centauri transmission. On December 18th, 2020, The Guardian published a story that should have shut down every other conversation on Earth. It did not. By the time the article appeared, the data it described was already 18 months old. The people who found it had decided, together, to say nothing. The Murray-Young radio telescope at Parkes, New South Wales, Australia, managed by the Commonwealth Scientific and Industrial Research Organisation, is one of the most sensitive radio receivers on Earth. Between April and May of 2019, it was running observations for Breakthrough Listen, the most comprehensively funded search for extraterrestrial intelligence in history, backed by $100 million from technology investor Yuri Milner, and operated by researchers at the University of California, Berkeley. The team was not expecting a discovery. That is almost always how it starts. The signal that appeared in the data was designated BLC-1. It arrived at 982.00 MHz. This number carries the full weight of what makes BLC-1 different from background noise. No natural astrophysical process produces a narrowband radio signal at a specific frequency. Lightning strikes, solar flares, pulsars, magnetars, rotating neutron stars, interstellar hydrogen gas, every natural emitter in the known universe broadcasts simultaneously across a wide range of frequencies. A narrowband signal at a single selected frequency is what a transmitter produces, not a phenomenon, not a natural process. An engineered device that has been designed to operate at a chosen frequency. BLC-1 was broadcasting at 1. It was also moving in a predictable way. The signal showed a frequency drift over time, a Doppler shift precisely consistent with a source located on a body orbiting a star. If you place a transmitter on a planet and observe it from Earth, the planet's orbital motion creates a measurable shift in the received frequency as the planet moves toward and then away from you in its orbit. BLC-1 showed that shift. The star in whose direction it arrived was Proxima Centauri, the closest known star to our solar system, at 4.2 light-years. Proxima Centauri is known to host at least one planet in its habitable zone. Proxima b was confirmed by the European Southern Observatory in 2016, orbiting at a distance where liquid water could exist on the surface. The Doppler characteristics of BLC-1 were consistent with a transmitter located on a body in that system. The Breakthrough Listen team then ran what is called the on-off test, the standard method for eliminating local radio frequency interference, as an explanation. The telescope pointed at Proxima Centauri, and the signal appeared. The telescope pointed away, and it vanished. The telescope returned to Proxima Centauri, and it reappeared. BLC-1 was tracking directionally with the star. This is the behavior of something coming from that point in the sky, not from any local source on or near Earth. The team spent the following 18 months attempting to identify a known terrestrial transmitter that could reproduce a directionally coherent narrowband drifting signal that passed the on-off test. No satellite, no aircraft, no ground facility was ever identified. The investigation ran in silence. No press release. No interim findings. No international notification through any of the formal SETI coordination channels that exist precisely for this situation. The only reason the public ever learned about BLC-1 was because Guardian science journalists Phoebe Weston and Ian Sample received a leak from within the investigation and published the story over Breakthrough Listen's objections. When Breakthrough Listen's statement arrived after publication, it classified BLC-1 as radio frequency interference. The statement acknowledged that no specific terrestrial source had been identified. It noted that the signal had not been detected again in follow-up observations, though it did not specify that Proxima Centauri had not been under continuous observation during those follow-up windows. One detection, directional, narrowband, drifting at the rate consistent with a planetary transmitter around the nearest star in the galaxy. Source unidentified. Held for 18 months. Released only because someone inside the team decided the rest of us should know. Number 2. The signal that Russia buried for 14 months. The Raytan 600 radio telescope stands in the Zelenchukskaya district of the Caucasus Mountains in Russia. Its name is a Russian acronym for Radio Astronomical Telescope of the Academy of Sciences. Its design is unusual among major radio observatories. A circular array of reflecting panels stretching more than half a mile across, operated by the Special Astrophysical Observatory of the Russian Academy of Sciences. It is one of the most powerful radio astronomy instruments ever constructed. In May of 2015, Ratan 600 was conducting routine survey observations of the northern sky, sweeping through the constellation Hercules. One of the objects in that survey was HD 164922, a G-type yellow dwarf star, the same stellar classification as our own Sun, located 94 light-years from Earth. Astronomers had been interested in HD 164922 since 2006, when the California Planet Search team detected a gas giant in orbit around it. On May 15, 2015, Radon 600 detected something else. The signal arrived at 11.1 GHz. This frequency is substantially higher than the bands typically targeted in SETI searches, which tend to cluster around the hydrogen line at 1,420 MHz. At 11 GHz, natural stellar emission processes are not expected to produce a coherent narrowband signal in the way the Ratan 600 team recorded. The power calculation was the detail that stopped them. If that signal originated from HD 164922 at a distance of 94 light-years, and if it was detectable at the strength they measured, the transmitter generating it would have had to be operating at an energy output far exceeding anything a natural astrophysical process associated with a star like HD 164922 should be capable of producing as a narrowband transmission in that frequency range. The team documented the detection. They did not report it. Not to any international astronomical body. Not to any SETI organization. Not to the SETI Permanent Committee of the International Academy of Astronautics, which exists precisely for the communication of candidate signals. The data sat in their archive for 14 months. In the summer of 2016, the detection was leaked. The source was Claudio Macconi, an Italian astronomer, affiliated with the International Academy of Astronautics SETI Permanent Committee, who received information about the signal through contacts within the Russian astronomical community and circulated it among researchers on the international SETI email list. Paul Gilster at Centauri Dreams, one of the most closely followed science communication outlets for deep space research, broke the story publicly in late August 2016. Within days, Seth Shostak at the SETI Institute was requesting observing time at the Allen Telescope Array in California to attempt independent confirmation. The response from the Special Astrophysical Observatory of Russia was prompt. A statement appeared describing the May 2015 detection as interference of terrestrial origin. The statement did not identify the terrestrial transmitter. It did not name a satellite, a ground-based facility, or any specific local source from which 11 GHz narrowband interference could have originated. It stated that the signal was not of cosmic origin and that the matter was resolved. Astronomers who responded publicly pointed out the immediate logical problem. Terrestrial radio frequency interference, by its nature, affects a radio telescope. Regardless of where the telescope is pointed, it originates from local sources and appears across all pointing directions. A detection that occurs when the telescope is aimed at a specific point 94 light-years away, in the direction of a star with a known planetary system, is the opposite of what terrestrial interference typically looks like. It looks like a signal from that direction. The Allen Telescope Array subsequently observed HD 164922. No repeat of the signal was detected. This is the same pattern as BLC-1. One detection, directional, anomalous, and no confirmed repeat during follow-up that was neither scheduled nor continuous. HD 164922b, the original confirmed planet, is a gas giant orbiting well outside the star's habitable zone. In 2016, the California Planet Search published the discovery of HD 164922c, a second, smaller planet, closer to the star. The announcement appeared in the same months as the leaked signal story, independently derived from years of prior radial velocity data. The star now hosts at least 2 confirmed planets. The signal from its direction on May 15, 2015 remains, without a confirmed source. HD 164922 is close enough to the Sun that on a clear night the naked eye can detect the general region of Hercules where it sits. A star similar to our own, 94 light-years away, with at least 2 planets sent something powerful enough to trigger an alert at one of Earth's most sensitive radio observatories. The people who received it decided, as a group, that 14 months of silence was the appropriate response. Number 3. The signal from nowhere. In 2003, the SETI at Home project had been running for 4 years. The project distributed the computational work of analyzing radio telescope data across millions of personal computers volunteered by the public worldwide, one of the largest distributed computing experiments ever conducted. The data came from the Arecibo Observatory in Puerto Rico, a 305-meter fixed-dish radio telescope that remained, until FAST was built in China, the largest single-dish radio telescope on Earth. Arecibo's beam swept the sky in strips as the Earth rotated, and SETI at Home broke the recorded data into small chunks and sent those chunks to be analyzed by computers belonging to anyone who had downloaded the software. By 2003, more than 5 million people in over 200 countries had participated. The project had processed more telescope data, with more computational power, than any centralized SETI effort could have matched. It had found nothing unambiguous. Then, in 2003, it found something. The signal designated SHGB 02+14A was identified in data recorded at the Arecibo Observatory during a sky survey. It arrived at 1,420 MHz, the hydrogen line frequency. This is not a coincidence worth dismissing. The hydrogen line is the electromagnetic frequency at which neutral hydrogen atoms naturally emit and absorb radiation. Hydrogen is the most abundant element in the universe. The hydrogen line at 1,420 MHz is therefore the cosmic constant, most likely to be known by any technological civilization, regardless of origin. It is the one frequency that can be derived from first principles, from the fundamental physics of the simplest element. This is precisely why SETI researchers identified it in 1959 as the most logical frequency on which intelligent transmissions might be sent or received. SHGB 02+14A arrived at exactly that frequency. Not near it, at it. The signal was detected 3 separate times from the same fixed point in the sky, located between the constellations Pisces and Aries. Each detection came during different passes of the Arecibo beam across that region. The source point showed a slight drift in frequency consistent with a transmitter orbiting a star, the kind of Doppler shift produced by a body in motion. The signal was roughly 2 times stronger than the surrounding noise floor when it appeared. It met several of the criteria that SETI protocols use to distinguish a candidate signal from background interference. It arrived from a fixed celestial direction. It repeated from the same position, and it registered at the hydrogen line frequency, where no natural astrophysical emission of this type is expected. There was one problem with the location. When astronomers examined the coordinates where the signal originated, they found no star. The position between Pisces and Aries, a position that produced this candidate signal 3 times from a fixed celestial direction, had no catalogued stellar object associated with it. No G-type star, no K-type star, nothing of the kind that would be expected to host a planetary system. Either the signal came from somewhere other than the apparent source position, which astrophysical analysis does not easily support, or it came from a region of sky where no identified transmitter should exist. The signal was reported in New Scientist in September 2004. Dan Wertheimer at the University of California, Berkeley, the chief scientist of SETI at Home, described it publicly as a candidate worthy of further observation. Arecibo scheduled additional observation time to attempt redetection. No subsequent detection matched the original 3 events from SHGB 02+14A's position. The signal was not confirmed. It was also not explained. No natural astrophysical mechanism was identified that would produce a repeating narrowband signal at the hydrogen line frequency from a fixed point in an apparently empty region of sky. The absence of a natural explanation and the absence of a subsequent detection are 2 separate facts. The first remains unresolved. The second is what happened to every other unexplained candidate signal in SETI history. A single or limited detection, no follow-up confirmation, and a silence that is treated as a resolution when it is nothing of the kind. 3 detections at the hydrogen line, a fixed celestial source with no associated star. A Doppler drift consistent with an orbiting transmitter. The signal that SHGB 02+14 most closely resembles, in frequency, directionality, and recurrence, is the signal that every SETI protocol was built to detect. What it does not resemble is anything produced by a known natural process. The data is in the archive. The location is in the catalog. No one has been able to say what produced it. Number 4. The announcement China deleted in hours. On June 14, 2022, the Science and Technology Daily published a story that lasted less than a day on the internet. Science and Technology Daily is the official newspaper of China's Ministry of Science and Technology, not a tabloid, not a fringe publication, but the state's own designated organ for communicating scientific developments to the public. The article described findings from FAST, the 500-meter aperture spherical telescope in Guizhou province, the largest filled aperture radio telescope ever built, with a collecting area larger than 30 football fields and a sensitivity that surpasses any other single-dish instrument on Earth. According to the article, FAST had detected, on 2 separate occasions, narrowband radio signals of a type consistent with potential extraterrestrial technological origin. The article named Zhang Tongji, chief scientist of China's extraterrestrial civilization search team at Beijing Normal University, as the researcher overseeing the analysis. Within hours of publication, the article was removed from the Science and Technology Daily website. Discussion of it on Chinese social media platforms was suppressed. The official follow-up, when it came, attributed the detections to radio frequency interference. The first signal had been detected during a survey conducted in 2020. The second was found in data from 2022. Both had been flagged by the research team as requiring further analysis before any conclusion could be drawn, a standard protocol for candidate signals that have not yet been ruled out as instrument artifacts or known interference. Sources: the fact that both signals were still under active investigation at the time of the June 2022 article is itself significant. It means they had not been ruled out. A signal that is definitively explained as terrestrial interference does not require further investigation. These two had not been explained. FAST operates at a sensitivity that no previous radio telescope could match. At its designed performance level, it can detect signals far weaker than those observable by other instruments, which means it is also more susceptible to detecting weak terrestrial interference and more equipped to distinguish genuine astrophysical signals from that background. The research team's own protocol involved comparing detections against a database of known radio frequency interference sources and removing any signal that matched. The 2 signals that were flagged by Zhang Tongji's team in the June 2022 article had, by that point, not been matched to any known interference source. That is what makes them candidate signals under SETI protocols. That is also the state at which the official announcement arrived under investigation, unexplained before the announcement was deleted. China's deletion of the article was rapid enough that international coverage relied on cached versions and screenshots. NBC News and The Guardian both reported the suppression within 24 hours. The coverage noted that Chinese scientific censorship in this area had precedent. An earlier FAST detection in 2020 had also generated brief public mention before being walked back to an interference explanation. The 2022 case is distinct because a named senior researcher with an institutional title was cited by name in the official state science publication, suggesting the article had passed editorial review at the level where such attributions are verified before publication. The interference explanation issued in the days after the deletion did not specify which terrestrial source the signals matched. No satellite, no ground facility, no known broadcast source was publicly named as the origin. The explanation followed the same structure as every other suppressed candidate on this list. The signal is not cosmic. The matter is resolved. No further information is available. The research team has not published a peer-reviewed paper on either detection. Zhang Tongji has not given a follow-up interview on the subject. FAST continues to operate, continues to survey, and continues to produce data that is not, in full, released to the international astronomical community. There are 2 separate detections from the world's largest and most sensitive radio telescope, flagged by a named research team as not yet explained, announced in an official government publication, and deleted within hours. The official explanation named no source. The researchers have said nothing further. Number 5. Little Green Men. In the summer of 1967, a doctoral student named Jocelyn Bell was working at the Mullard Radio Astronomy Observatory at Cambridge University, analyzing paper chart recordings from a radio telescope array she had helped build across 4.5 acres of English countryside. The The telescope was designed to study quasars. Bell was the person who checked its paper output, a task that required reading chart after chart of signal data by hand. In late July of 1967, she noticed something in the data that did not belong. A signal was repeating at an interval so precise, so machine-like, so utterly unlike any known natural source, that Bell flagged it immediately and brought it to her supervisor, Anthony Hewish. What Hewish and Bell then did was not announce it. They said nothing. For months, they said nothing at all. The signal was arriving from a fixed point in the sky. It repeated every 1.3373 seconds, not approximately to 4 decimal places, the period held. No natural astrophysical process known to science in 1967 produced a signal that repeated at a fixed interval with that degree of precision. Stars do not pulse with clockwork regularity. Gas clouds do not oscillate at machine-like rates. Cosmic radiation does not tick. The Cambridge team knew this. Hewish knew this. Bell knew this. They began logging the detections in silence and debating internally what they were looking at. The signal was so regular that, when they had ruled out every obvious instrumental explanation and every local interference source, the team assigned it a name, LGM-1. The initials stood for Little Green Men. Bell later described the period that followed with characteristic precision. The team discussed what to do if the signal was confirmed to be artificial. They discussed whether to announce it. They discussed what the implications would be for the world if the announcement was that humanity had detected a signal from another civilization. They discussed the effect on Bell's doctoral work, which would become, in that scenario, the most consequential piece of scientific documentation in human history. What they did not do was announce it. The paper charts were kept within the group. The data was not shared with the international astronomical community through any of the channels that existed for exactly this purpose. The Cambridge team held it. In December of 1967, Bell found a second signal of the same type from a different part of the sky, then a third, then a fourth. The existence of multiple sources, each pulsing at a different rate, but each with the same clockwork precision, led the Cambridge team to a new hypothesis. What they were observing was not a single alien transmitter, but a natural phenomenon, an entirely undiscovered class of astronomical object. The theoretical framework that emerged was the rotating neutron star, a stellar remnant so dense that a teaspoon of its material would weigh billions of tons, spinning at rates that produced precisely timed radio pulses as the beam swept past Earth like a lighthouse. This framework, which came to be called the pulsar model, was published in Nature in February of 1968, 6 months after Bell's initial detection. The pulsar explanation became the consensus and has remained it. Thousands of pulsars are now catalogued, and the rotating neutron star model has been confirmed by independent lines of evidence. This is not disputed. What is less often discussed is what the Cambridge response tells us about how institutions handle the discovery of a signal from space that has no natural explanation at the moment of its discovery. When Jocelyn Bell found LGM-1, neither she nor Hewish nor anyone in that group knew it was a neutron star. They knew it was the most regular radio signal ever detected from space. They knew it had no explanation available to them, and they chose 6 months of institutional silence over immediate disclosure. Bell was not awarded the Nobel Prize when Hewish received it in 1974 for the pulsar discovery. She has spoken publicly, in multiple interviews and in published essays, about the internal dynamics of that period. The signal that she found and was told to keep quiet about is now the foundational discovery of an entire branch of astrophysics. What she held in her hands in the summer of 1967, before the neutron star model existed, was a radio signal from space, repeating with mechanical precision that no human technology had produced and no natural process could explain. The institution's response was 6 months of silence. Number 6. The document the NSA kept classified for 45 years. In 1966, Howard Campaign was a senior mathematician at the National Security Agency of the United States. Campaign's career at the NSA had begun during World War II when he worked on breaking German and Japanese codes. By the 1960s, he was one of the agency's most senior cryptanalysts, a figure with the kind of institutional standing that allowed papers he wrote to be published in the NSA Technical Journal, a classified internal publication distributed only to personnel with the appropriate clearance. In 1966, Campaign published 2 papers in that journal. Together, they would remain classified for 45 years. The papers were titled extraterrestrial intelligence and communications with extraterrestrial intelligence. The declassified versions released in 2011 describe, in rigorous mathematical language, the framework for decoding a structured communication received from a source outside Earth. The first paper constructs the theoretical basis. What properties a communication from an extraterrestrial intelligence would need to have for a recipient with no prior knowledge of the sender's language or mathematics to begin decoding it, and how those properties would manifest in the signal's structure. The second paper applies this framework. It does not frame the problem as hypothetical. It describes a sequence of 29 messages and the process of extracting meaning from them. It does not state that the messages were fictional, it states that they were received. The NSA held these documents under classification for 4.5 decades. Dr. John Greenewald, Jr., founder of the Black Vault, a private archive that systematically files Freedom of Information Act requests, with federal agencies submitted requests for NSA documents related to UFOs and extraterrestrial intelligence beginning in the late 1990s. The NSA acknowledged the existence of these documents and declined to release them for years, citing national security exemptions under FOIA. The documents were finally released in 2011 with redactions. What remained after declassification was Campaign's mathematical framework and the explicit description of 29 received messages. The nature of the classification is the detail that has not been adequately addressed in any official communication. The NSA does not classify mathematical exercises or theoretical papers. It classifies information whose release would damage national security. The agency's mandate is cryptography, the making and breaking of codes, the interception and analysis of communications. A theoretical paper about how to decode a hypothetical extraterrestrial transmission would be a curiosity, interesting perhaps for its intellectual scope, but not material that would sit in a classified journal distributed only to cleared personnel for 45 years. The NSA classified Campaign's paper because its contents met the threshold for classification. What that content describes is the decoding of 29 received messages. A companion paper by Lambros Kalamajos, also a senior NSA cryptanalyst and Campaign's colleague at the agency, was released alongside the Campaign documents. Kalamajos had published extensively within the NSA on communications theory and was, like Campaign, one of the founding figures of the agency's cryptologic culture. His paper on extraterrestrial communication was equally specific in its framing, equally mathematical in its approach, and equally held under classification for the same period. Two of the NSA's senior cryptanalysts, in the same year, producing classified papers on the decoding of non-hypothetical messages from outside Earth. The standard explanation for these documents is that they represent theoretical exercises, thought experiments conducted by mathematically inclined intelligence professionals exploring the abstract problem of first contact. This explanation accounts for why they were written. It does not account for why they were classified. Theoretical exercises in mathematics do not require FOIA litigation spanning more than a decade to obtain. They do not carry national security exemptions under federal law. They are published, shared, discussed, and eventually become textbook material. The Campaign papers were none of these things for 45 years. The NSA Technical Journal is not a venue for speculation. Papers published in it are operational documents, analyses, frameworks, and findings produced by working intelligence professionals for the institutional use of the agency. That is what the classification structure of that publication is designed to contain. What the Campaign papers describe, in the language of a working cryptanalyst rather than a science fiction writer, is the receipt and decoding of 29 structured messages. The documents exist. They are in the public record. The classification that held them for 45 years has never been formally explained. Number 7. The burst that repeats on a schedule. In 2007, Duncan Lorimer at West Virginia University and Matthew Bales at Swinburne University of Technology in Australia were searching through archival data recorded by the Parkes Radio Telescope in Australia when they found a single bright radio burst that had been sitting in the archive unnoticed for 6 years. The event was intense, milliseconds long, and arrived from outside the galaxy. It was the first fast radio burst ever identified. For 9 years after that discovery, every additional fast radio burst found was a single event, one flash, one position in the sky, and then silence. The prevailing models assumed this was inherent to the phenomenon that whatever produced fast radio bursts destroyed itself in the process, the way a firecracker cannot repeat. Then, in 2016, a team led by Laura Spittler at the Max Planck Institute for Radio Astronomy published data from the Arecibo Observatory in Puerto Rico showing that the fast radio burst designated FRB 201211002A, first detected in archival data from 2012, had appeared again, and again, and again. For the first 4 years of the FRB catalog, repetition had been the one feature no source exhibited. FRB 201211002A had been repeating. The source was eventually localized to a dwarf galaxy, approximately 3 billion light-years from Earth, one of the most distant objects ever confirmed to produce a detected signal. The galaxy is small, metal-poor, and actively forming stars. From that distance, across 3 billion light-years of intergalactic medium, FRB 201211002A has been detected hundreds of times. Its pulses vary in duration, intensity, and arrival rate. They cluster in active windows separated by silent windows, hundreds of bursts from the same source. The physical mechanism capable of producing a repeating, directed radio signal across 3 billion light-years without destroying itself in the process is not one that astrophysics had previously been required to account for. In 2020, 2 independent research groups, one led by Kaustubh Rajwade at the University of Manchester, one led by Marilyn Crucis at the Max Planck Institute, analyzed the timing of FRB 201211002As, detected bursts across the full observation record, and found the same result. The source shows a periodicity of approximately 157 days. For roughly 90 days, it is active, producing detectable bursts. Then it goes silent for approximately 67 days. Then it becomes active again. The cycle has held across multiple years of observation. The 2 groups published their findings independently and arrived at the same number from the same data, 157 days, plus or minus 1 day, repeating. Natural candidates for a periodic 157-day cycle in an astrophysical radio source are limited. A precessing magnetar, a rotating neutron star with an extreme magnetic field, wobbling on its axis, would produce a periodic beam direction change, but the precession periods calculated for magnetars of the relevant type do not easily reproduce a cycle of this specific duration or duty cycle. A binary system in which one object periodically blocks or enhances the other's signal could produce periodicity, but no companion has been identified, and the bursting pattern during the active window does not match orbital modulation models. The orbital configuration that would produce a 157-day cycle for a compact object in a plausible binary system does not correspond to any confirmed pairing in the host galaxy. What a 157-day period does resemble, structurally, is a schedule, a consistent cycle of activity and silence repeated across multiple years from a fixed extragalactic source. The 90-day active window, 67-day quiet window pattern is stable enough that researchers can now predict, within days, when FRB 201211002A will next be detectable. This predictability is not a property of most natural astrophysical phenomena. Lightning does not keep a schedule. Solar flares do not recur on a calendar. Magnetar outbursts are stochastic events, driven by internal stress buildup in the stellar crust. A source 3 billion light-years away that can be scheduled in advance by astronomers on Earth is the kind of source that asks for an explanation the natural models have not provided. FRB 201211002A has been active since at least 2012. It will be active again. The 157-day cycle predicts when. 3 billion light-years away, something is operating on a recognizable timetable, observed, documented, published, and still without a model that accounts quantitatively for both the repetition and the period. Number 8. The same signal from 234 different stars. In 2012, Hermano Borra, an astronomer at Laval University in Quebec, published a paper in the Astronomical Journal proposing what a laser communication signal from an extraterrestrial civilization would look like in the spectrum of a star. The argument was straightforward. If a civilization wanted to communicate with observers using optical rather than radio frequencies, the most efficient method would be to embed rapid pulses of laser light into the spectrum of their host star. The pulses would be too fast and too brief to be visible to the naked eye or to most conventional astronomical instruments, but they would be detectable in high-resolution spectroscopic data as a periodic modulation, a repeating variation in the star's light at a specific, very high frequency. Borah calculated the precise mathematical signature such a signal would leave in stellar spectra. He published the prediction. Nobody found the signal. Then, 4 years later, Borah and his graduate student Eric Trottier went looking for it. The Sloan Digital Sky Survey had, by 2016, accumulated high-resolution optical spectra for approximately 2.5 million stars. It is one of the most comprehensive stellar spectroscopic databases in existence. Borah and Trottier analyzed those spectra, specifically searching for the periodic modulation pattern that Borah had mathematically predicted in 2012. They found it. Not in one star, not in a handful, but in 234 stars. The results were published in Publications of the Astronomical Society of the Pacific in October 2016. The 234 stars, showing the modulation, are distributed across the sky. They sit at different distances from Earth, ranging from nearby to hundreds of light years away. They are not in the same region of the galaxy. They are not gravitationally associated with one another. They are not in a known cluster or stream. Each star is a separate, independent source. What they share is this. Embedded in the spectroscopic signature of each one is the same periodic modulation pattern at the same frequency, consistent with pulses at a rate of approximately 10 to the 14th hertz, a number that falls within the range of laser pulse rates that Borah had predicted in 2012 as what technological communication would look like. The modulation cannot be explained by the stars themselves. Stellar spectra do not spontaneously produce periodic high-frequency modulations of this type. The physical processes inside a star, nuclear fusion, convection, magnetic activity do not generate the specific pattern Borah and Trottier identified. Borah and Trottier examined alternative instrumental explanations and found no consistent artifact in the Sloan equipment that would produce the observed pattern across multiple observing runs and instruments. The signal appeared in data collected at different times, under different observing conditions, from multiple independent observations of the same stars. The SETI Institute responded quickly. A formal statement acknowledged that the Borah and Trottier finding was interesting and warranted follow-up. The statement also noted that it was probably the result of a systematic error in the data or analysis. No specific systematic error was identified. The SETI Institute did not schedule dedicated follow-up observations of the 234 stars. Borah responded to the criticism in a subsequent paper, maintaining that the modulation was real and that the instrumental explanations proposed by critics did not match the observed pattern. The exchange produced no consensus. The 234 stars were not intensively monitored. What the finding requires, if it is not instrumental, is a source capable of modulating the spectral output of 234 separate stars in the same way. Not two stars, not a local cluster, 234 independent stellar systems distributed across the galaxy, each bearing the same optical fingerprint that Ermanno Borah predicted in 2012 as what laser communication from a technological civilization would look like in high-resolution spectroscopic data. The Sloan Digital Sky Survey data is publicly available. The 234 stars are in it. The modulation that Borah and Trottier identified has not been retracted, not been traced to a specific instrument error, and not been reproduced by any natural stellar physics. No telescope has been dedicated to watching those 234 stars for follow-up detections. They sit in the catalog. Their spectra carry the pattern. The equipment that could answer the question exists. The observation has not been made. Number 9. The pattern inside the static. In 2007, Duncan Lorimer at West Virginia University and Matthew Bales at Swinburne University of Technology in Australia were searching through archival data recorded by the Parkes Radio Telescope in 2001 when they found a single, bright radio burst that had been sitting in the archive, unnoticed for 6 years. The event was intense, milliseconds long, and arrived from outside the galaxy. It was the first fast radio burst ever identified. For the following 7 years, every additional fast radio burst discovered was a single, non-repeating event from a different position in the sky. By early 2015, the total catalog contained 11 events. Each had its own measured dispersion measure, the number that encodes how much the signal's frequency components have been spread by electrons in the intergalactic medium during transit. Dispersion measure is a proxy for distance and path. The more electrons a signal passes through, the higher the dispersion measure, and the farther and denser the medium it has traveled through. Each of the 11 known fast radio bursts had traveled through a different region of intergalactic space. Their dispersion measures were all different from one another. In January of 2015, Michael Hipke at the Sonneberg Observatory in Germany and a group of collaborators submitted a paper to the Astrophysical Journal that described something no one had expected to find in those 11 different numbers. 4 of the 11 dispersion measures were exact integer multiples of the same base value, 187.5 parsecs per cubic centimeter. These 4 signals had arrived from 4 different positions in the sky. They had traveled through 4 independent paths through intergalactic space, encountering 4 different densities of electrons across 4 different total distances. For 4 independent measurements across different cosmic paths to produce values that are exact integer multiples of the same unit is not what random sampling of the universe produces. Hipke and his colleagues calculated the probability of this relationship arising by chance, approximately 5 in 10,000. The implications split into 2 categories. The first is a systematic error, some shared artifact in how the observations were made or how the dispersion measures were calculated, producing a correlated result across the 4 events. The second is that the relationship is real, in which case it requires an explanation. A real integer multiple pattern in dispersion measures could indicate that the sources are preferentially located at specific distances from Earth, that something clusters the origins of fast radio bursts at defined ranges. It could also indicate that the signals were engineered, that a sender chose the distances from which to transmit such that the dispersion measures, as was received at Earth, would carry a recognizable mathematical structure. The integer sequence is among the simplest patterns a transmitter could embed in a signal. It is the kind of structure a sender would choose if it wanted the mathematical relationship to survive billions of light-years of intergalactic travel and be recognizable on the other end without requiring prior knowledge of the Fardian-state-decided sender's mathematics. Hipke's paper was published. Vini Ravi at the California Institute of Technology published a formal response in the same journal, arguing that the statistical significance of the integer relationship was sensitive to the assumed value of the electron density of the interstellar medium, a quantity that carries real uncertainty, and that with different, reasonable values for this parameter, the pattern diminished. Hipke and his collaborators replied, "The exchange continued without resolution. The core problem was the sample size. 11 events is a small enough number that statistical arguments about patterns within it are inherently fragile. No definitive verdict was reached. By 2025, the total catalog of fast radio bursts exceeds 5,000 events, collected by CHIME, FAST, Parkes, and other instruments. The specific integer multiple relationship identified in the original 11 does not appear at the same statistical significance in the expanded dataset. This is either evidence that the pattern was a coincidence or evidence that it represents a specific subset of fast radio bursts, a structured component embedded within a much larger population of naturally occurring events, detectable as a pattern only when the naturally occurring ones are relatively few in number. What did not change is this. The 4 original fast radio bursts with integer multiple dispersion measures remain in the dataset, arrived from different positions in the sky, and their relationship to the base unit of 187.5 has never been traced to a systematic measurement error in the specific instruments that recorded them. 5 chances in 10,000 in the original data, not explained away, just set aside as the catalog grew large enough to make them look small. Number 10. The star that has been dimming for a century. In 1890, astronomers at the Harvard College Observatory began photographing the night sky onto glass plates. The plates were stacked, cataloged, and stored in a collection that grew across decades into one of the most extensive photometric archives in the history of astronomy, over 500,000 images spanning more than a century of the sky's recorded brightness. Stars in the Harvard collection have brightness records stretching back to the administration of Grover Cleveland. The plates were irreplaceable. They were also, for most of the 20th century, largely unanalyzed. By the time the digital era arrived and the plates began to be systematically scanned and digitized, the data they contained had been sitting in physical storage, accessible, real, physical evidence captured on glass for generations without anyone asking the right questions of it. The star now designated KIC 846285 sits in the constellation Cygnus, approximately 1,400 light-years from Earth. In 2009, NASA's Kepler Space Telescope began monitoring it continuously, along with more than 150,000 other stars, measuring their brightness with a precision no ground-based telescope could match. The data from Kepler is public. In 2015, Tabitha Boyajian at Yale and a team of citizen scientists working through the Planet Hunters project identified KIC 846285 as exhibiting the most bizarre light curve in the entire Kepler dataset. The star was dimming in ways that no known natural or astrophysical process could account for. It dimmed by up to 22% over periods of days far too deep and too asymmetric to be a transiting planet, which produces dips of no more than 1% and returns to baseline symmetrically. The dips had irregular shapes, irregular depths, and irregular timing. Some were single events, some were clustered. Nothing in the 4-year Kepler record matched any model of natural stellar variation or known orbital mechanics. The immediate attention that followed the 2015 Boyajian paper concentrated on the Kepler record. It was the astronomer Bradley Schaefer at Louisiana State University who went further. In 2016, Schaefer published a paper in the Astrophysical Journal Letters reporting what he had found when he examined the digitized Harvard photographic plates. He was not looking for what he found. He was examining the archival data to calibrate the Kepler observations against historical baselines. What the Harvard plates showed was that KIC 8462852 had been continuously dimming since the earliest plates available, since before the Wright brothers flew, since before the automobile was common, since before the First World War. The star had lost approximately 16/100ths of a magnitude of brightness per century across the full span of the archival record. In total, it had dimmed by approximately 20% over the course of 100 years of human observation. The evidence for this had been sitting in the Harvard collection the entire time. The dust explanation circumstellar material in a swarm of comets or a debris disk had been the leading natural proposal since the Boyajian paper. Subsequent infrared observations ruled out a warm dust disk. Extended dust models were proposed as an alternative. But here is the problem that Schaefer's analysis created for every dust model. Dust in orbit around a star is not static. Orbiting material spreads, dissipates, and evolves dynamically over the timescales involved. A dust configuration sufficient to produce 20% secular dimming continuously across a century of observation, while simultaneously producing the irregular deep transits seen in Kepler data, requires a specific, sustained distribution of material that no dust model published to date has reproduced quantitatively. Jason Wright at Penn State, one of the astronomers who had suggested the megastructure hypothesis in 2015, noted in multiple published responses that the secular dimming Schaefer identified makes the natural explanations substantially harder, not easier, than the Kepler data alone suggested. The star is dimming. It has been dimming since at least 1890. The Harvard plates are physical glass negatives that encode this. They are not controversial instruments. They are not speculative analysis. They are brightness measurements of a specific star taken over a century, sitting in a box in Cambridge, Massachusetts, while the star continued to do whatever it has been doing since before any human alive today was born. 1,400 light-years away, 130 years of documented darkening, no model that accounts for both the secular dimming and the irregular deep transits simultaneously. The evidence has existed since the plates were first made. We had it the whole time. We simply had not looked. From BLC-1 to the Harvard plates, from a signal held for 18 months to data held in a physical archive for over a century, every item on this list follows the same shape. Physical evidence, documented in real instruments by real researchers, and then set aside without explanation, or explained away without an explanation that holds. Something has been reaching toward us from the dark for a long time. The record of it is in our own archives. If you want to see more videos like this, click the video on screen now and make sure to subscribe.